Good day everyone. Welcome to the course on biological data analysis and visualization with R. In the last two classes, we have talked about logistic regression and we have applied logistic regression for classification of data sets. In this class, we will be talking about another method which also helps us in classification. It is called decision trees. So, I will first introduce what is decision trees, how these decision trees are constructed, and then followed by that in the subsequent class we will be doing some hands on, we will apply decision trees and we will see the structure of decision trees. Okay, so, we will talk about decision trees first, right, and the components of decision trees, and the second part will be very briefly discussing how these decision trees are constructed, and this is where we will see some of the limitations that we have for linear regression or logistic regression, where we have to assume linear relationship between the response variable or the probability and the independent variables. So, this does not hold, right. So, you can this kind of structure decision tree models can actually capture the non-linearity in the data, right, non-linear relationship between independent variables and the dependent variable. Okay, so, that is the agenda for this class. We will first start with decision tree. So, a decision tree is an algorithm that enables decision making with a tree like structure, right. So, this is something we will see in a moment how the structure looks like and how decisions are made. And decision trees can be used for classification as we have seen right before. In logistic regression, we can use this kind of algorithm for sample classification or data classification, as well as for regression models, right, like linear regression, where you want to predict the values of the response variable. So, this is also possible here with this algorithm. So, let us now look into how does a decision tree look like, okay, and as the name suggests, this is a tree like structure, right. Here you have kind of start here and then we have kind of branches, right. So, we have branch. So, we have now branching here and we have these two branches that are going right in two directions. From here we have branching again, right, we again have a tree structure and so on, and finally, we arrive at this end here, right. So, this is how it looks like a tree, right, and what are the components that are defined here. So, what you can see, this tree decision tree is composed of nodes, right. So, here we have these nodes in different colors and the edges, right. So, you have these edges here or branches here, right. Specifically, we also classify these as the root node, right, where we start this classification process or the decision process. And as you can see here, you probably see in very small letters if something is written, right, yes or no. So, at every node we are making decisions. Okay. So, there is a specific criteria and we are saying whether the sample satisfy that criteria. Yes, you will have to follow this branch, no, will follow this branch, right. So, this is how we are making decisions, and this is something that we apply for sample classification as well as for regression. Okay. And then here we have these internal or decision nodes, right. Again, internal nodes, at every node we are making some decision, and then finally we arrive at something called leaf nodes. Okay. This is where we are not making any more decisions, right, and this is where we stop the tree, right. This is the end. Okay. So, these are called leaf nodes. Okay. And then we, of course, as I said, we have branches, right, and at every node we have branching. We are making decisions, we have yes branch and no branch. We also can measure tree depth, right, and this is defined as maximum distance between the root node and a leaf node. Okay. So, if you have to, let us say, consider tree depth in this tree, specific tree, we have to consider the maximum distance between the root node and a leaf node. And as you can see, the maximum distance is perhaps through this path, right. So, here we have these many nodes, intermediate nodes, right, and this will give us the maximum distance or tree depth. Okay. Now, why are we discussing this tree depth? Because this is something that will come up, right. This is something that will be important when you talk about overfitting again. Now, what are the applications of decision trees? As I said, we can use decision trees for data classification or sample classification, and these are referred to as classification trees, and as before we apply these for classification of biological samples. which we have already seen in case of logistic regression, some of the real data sets where we actually can apply these classification trees for classification. But we can also apply decision trees for regression purpose, right, where we want to predict values of the response variables, which we did in case of linear regression. Okay, so now we understand the structure, right, and applications of decision trees. Let's now look into how we can construct a decision tree. Right. So, if we have data, how can we construct a decision tree? Okay. And there are two key questions or two parameters that we have to deal with when you are going to build a decision tree. Is how do you choose the feature for the root node, right? So, root node, when you say this is root node, this is a feature, right? In this case, you have seen this is a gene name, that is the root feature, right, or root node. For any data, we have to first identify what is the root node, right? How do you, out of let us say 20 features or 100 features, which one is the root node, right? How do you identify that, or how do you define that? Whether you are building a classification tree or a regression tree, you have to define that. Okay, this is something that we have to deal with. And the second is how do you choose these threshold values for taking decisions, right? How do you say, okay, this gene expression should be greater than 40 or greater than 20 and so on? How do you choose that value 40, okay, for cutoff, right? Is there any basis for that? And as we will see now is yes, there is a basis for all of this, right? How do you choose a root node, or how do you actually choose these threshold values? Okay. We will very briefly discuss this so that you have some idea in the tree construction, right, how these decision trees are made, and this is something that might be helpful, right, when you try to interpret the results that we see at the end, right, when you actually work with decision trees on real data sets. Otherwise, of course, we can just simply use our commands and run decision trees, but it is what I think could be helpful to know the basis of these tree constructions. This will help you interpret the data or interpret the results better. So, for choosing root node, we can use three type of criteria. We will talk about only these three, and of course, think about other as well. So, these are the very popular ones. So, first one is called gene impurity, the second is called entropy, and the third is information gain. Okay, so, we will very briefly discuss each of these criteria. What is gene impurity, how do you calculate with a very simple data, okay, so that you have a good idea about how do you calculate this. So, gene impurity is defined by this formula. So, 1 minus summation I equals to 1 to k pi square. Okay. So, what is pi? It is probability that a sample belongs to class I at a node. Okay. So, when you are building a decision tree, that is sample at a node belongs to class I, that is the probability, and then k is the number of classes that we have in the data, right. So, if it is a binary classification, we have 2 classes, so k equals to 2. If it is multinomial classification, we will have k equals to 3, 4, etc. And one of the properties of gene impurity is that the value lies between 0 and 0.5. Okay. So, as you will see, right, when you go into that example, you will see it will always lie between 0 and 0.5. When value is 0, right, z equals to 0, that means the node is pure, right. All samples of that node belong to the same class, right. Why is it important is that if you achieve this, right, z equals to 0, that means you have achieved perfect classification, right. The node is all the samples in that node, they belong to the same class. So, now we have identified some criteria that will give you pure classification, right. You are getting pure classes, right. So, this is something that is very, very important, and this is something that we will see, right, how this actually tells us, right, whether our classification model is good or not. Okay. So, let us now take a very small example data, right, where we have for our demonstration. This is of course not real data, just to see how this works, how we can calculate gene impurity, and then we will also illustrate how we can use gene impurity to identify the root node, okay, with a very small data set, and then of course we will do the hands on and we will see how this works on actual real world data sets. Okay, so, here we have samples, 4 samples. Let us imagine patient 1 to 4, and we have the classification for different cancer types. Okay. So, LML, BRCA, BRCA and LML. So, 2 samples belong to LML class and 2 samples belong to BRCA class. So, we have to calculate gene impurity for this data. So, k equals to 2 classes, right. So, we have 2 cancer types, so 2 classes, and the probability, right, for so we have equal number of samples of each class. So, the probability is 0.5, 0.5, right. So, P1 is 0.5, P2 is 0.5, we have 2 classes. So, gene impurity is defined, as I said, is 1 minus summation Pi square. So, for P1, P2, right, we just take the 0.5 square plus 0.5 square, and so 1 minus this will become 0.5. That is the maximum value of gene impurity, right. So, when you get this maximum value is that we have in a data set, we have all classes represented equally, right. So, it is a very heterogeneous or impure data set, right, as the term gene impurity implies, right. This is an impure data set, means there is a lot of class mixing, right. The data from different classes are mixed together and they are in almost equal proportion, right. So, that is what it is. Now, let us now change this and change this data set and say let us all samples belong to one class only, right, LML, LMN, right. And so, patient 1 to 4 they all belong to this one cancer type, and then now we want to calculate this gene impurity. Here k equals to 1 and P1 is also 1, right, because there is no other class here in this node, and gene impurity will be simply be 1 minus 1 square, which is 0, right. When g equals to 0, this means data is pure, right. So, as you can now understand, lower value of gene impurity refers to highest purity, right. So, if you have lower value of g, you get higher purity, right. This is what we have seen here, right. When g equals to 0, we have all the samples belonging to same class. When g is equal to 0.5, we have a heterogeneous data. Okay, so, now we understand how we can calculate gene impurity, and we now take this forward and we can now use this to identify root node in a again and in an example data set. Okay. Now, we have kind of increased this data set. Now, we have these 5 patients, right, data. We have again cancer types, and we have gene A expression levels and gene B expression levels. Okay. How do you identify the root node? The root node is identified as the feature that leads to highest overall purity and lowest overall G value, right, as we have just learned. After branching is the root node. Okay. So, again I will read this again, so that we understand very carefully here. The feature that leads to the highest overall purity after branching is the root node. Okay. And this is something we will again illustrate with this gene A, gene B example. So, first we will consider gene A as the root node and gene B as the root node, and then we will see which one is likely to be the root node. Okay. So, in this first step, let us use the gene A as the root node and the criteria be gene A greater than 40. Okay. So, for now let us assume that we know like okay 40 is the criteria, but then we will see, right, this number can vary and how do you again identify that number. Okay. So, if we consider this criteria gene A greater than 40, what will happen is we have again gene A expression greater than 40, right, yes, no, right. So, we are taking decisions now, and if it is no, then we have this node 1 here where we have patients 2 and 3 will come under this, right. So, if you look into the expression value, so this patient 2 expression of gene A and patient 3 expression of gene A is lower than 40. So, they will come under this node. And if you consider the ES branch, right, we have patients 1, 4, 5 in node 2. Now, what you see is in patient 2 and 3 they are both of this BRCA class, whereas patient 1, 4, 5 they are all of LAML class. Okay. Now, what we are going to do is, as I said, after branching we will calculate the overall gene impurity or overall G. Okay. To calculate this overall G, let us now look into this tree structure. So, for node 1 we have to first calculate G, and for node 2 we will have to first calculate G. Okay. So, for node 1 the G is 0, right, G1 is 0 because we have only one class, right. As we have seen, if we have only one class, gene impurity will be 0. Similarly, for node 2 again we have only one class LAML, so this will be 0 again. How do you calculate this overall G? For if we take root node A as the root node, is given by this formula N1 by N times G1 plus N2 by N times G2. So, N1 is number of samples in node 1, N2 is number of samples in node 2, and n is simply n1 plus into the total number of samples that we have. So, let us put this formula, right, and here everything is 0. So, it does not really matter. So, be 2 by 5 times G1 plus 3 by 5 times G2, and G1 G2 they will be 0. So, the total value overall G is 0. Okay. So, if we choose A as the root node and the criteria as A expression of gene A is greater than 40, the overall gene impurity is 0. Now, let us choose gene B as the root node and the criteria be gene B greater than 30. Okay. So, just as an example, again you might ask, like, why 30, how do you choose this 30, that we will talk about a bit later. If we do that, then we have no and yes again, we have to take these decisions. So, gene P expression greater than 30, patients 1 and 5. So, if you look at this, patients 1 and 5 they will come under root node no, right, no branch would be 1 and 5. In yes branch you will have patients 2, 3, 4 in node 2. Now, if you look into the class information for these nodes, so in node 1 the patients, both patients are of LAML class, but in node 2 now we have 2 patients in BRCA class, 1 patient in LML class, right. So, this is something that you can see, right, we have 1 sample in LML class, 1 patient. We will follow the same steps as before. We first need to calculate node 1 and node 2 gene impurity, and then we will calculate the overall G value. So, node 1 G1 is 0 simply because node 1 has only 1 class. For node 2 it is not 0 anymore, because now we have 2 classes represented within node 2. Okay. So, for that we use this formula now for gene impurity is 1/3 square, right. As you remember, this is pi square. Pi is a probability that a sample belong to a specific class or class I in that node, right. So, here we have 1 sample that belongs to this one class and 2 samples belong to other class. So, that is why it is 1/3 square minus 2/3 square, and the value we can calculate whatever the outcome is, it is not 0, right, it is non-zero, that is important. And then we can now calculate the overall G using the same formula n1 by n into G1 plus n2 by n into G2, and for G1 it is 0, for G2 is non-zero. So, we get some value, positive value for overall G. Okay. Now, we have tried both node A and node B as our root nodes, right. So, overall G, if we choose A as the root node, then the value is 0. If we choose B as the root node, then the overall G is 0.27. It is a non-zero value, whatever that value is actually. Now, as we have talked about, is the node or the feature that gives us the lowest impurity or lowest G value. So, that will be the root node, right. So, here gene A is giving us the lowest impurity or the highest purity, right, and overall G is the lowest. So, the gene A greater than 40 as the decision criteria would be our root node. Okay. So, this is something that will go in the background when you actually analyze your data with decision tree, right. So, we now understand some of the basis of this formation of decision tree. We might still ask, right, why are you choosing this 40 or 30, how we are choosing that. So, that is something we will discuss a bit later, but first I will discuss another measure that we can use very similar to gene impurity, is called entropy. So, this is again a measure of purity at node, but the formula is slightly different. Here it is minus summation I equals to 1 to k pi log pi, right. So, we have to now deal with this again, right, pi, which is the probability that a sample belongs to class I as before, and k is number of classes that we have in the data. Okay. And again what we have seen like gene impurity that lies between 0 and 0.5, here the value lies between 0 and 1, right. And again, if you have 0 value means you have highest purity, if you have 1 value, that is the lowest purity, right. So, that is something that again very similar in terms of property to gene impurity. How do you use this feature to identify the root node, right. So, again we take the same example and we can see whether we come up with the same results. Okay. The criteria is the feature that leads to highest overall purity and lowest entropy after branching is the root node. Very similar criteria as gene impurity. So, now the formula, the calculation is slightly different, but apart from that the criteria etc., they are all same. So, let us now illustrate this again with the same data set and see what happens we will again use these two criteria that we have chosen earlier, right. We will use gene A as the root node and the criteria be gene A greater than 40. So, then we get this branching again, right. We have seen this example. If we use the first criteria gene A expression greater than 40, in the no branch you will have patients 2 and 3. So, these node 1, both samples belong to BRCA class. In node 2 we have patients 1, 4, 5, they all belong to LAML class. We can again calculate this entropy for each of these classes, and as you will see E1 is minus 1 log 1, right, because we have only one class, and similarly for node 2 we have one class. So, this is 0. So, the overall entropy again very similar formula. Instead of gene impurity we just have N1 by N times E1 plus N2 by N times E2. Okay, so, then we can calculate, and the overall entropy is 0 here. Okay. Let us use gene B as our criteria, right. So, here it is, right. Again we have the same criteria, gene B greater than 30, and that gene B, this is the criteria as the root node, and we have very similar structure. Again we have seen this before. Node 1 we have patients 1 and 5, both belong to the same class LAML, but in node 2 now we have patients 2, 3, 4, we have two different classes, right. So, we have BRCA as well as LAML, one sample belonging to LAML class. We can calculate this individual entropies for node 1 and node 2. For node 1 is 0 because there is only one class. For node 2 it is not 0, there is a specific value because we have two classes now. So, we have 1/3. So, we have to take this summation pi log pi we can calculate, and then a minus sign is there. So, we get some positive number, here it is 0.28, but again this does not matter the absolute value, this is a positive number. If we have that, then we can calculate this overall E with for root node B and the criteria B greater than 30. We have a very similar formula, and then we can calculate. So, 2 by 5 into 0, E1 is 0, E2 is a positive number, and then we have overall E which is non-zero, right, it is a positive number. So, if we now go back and compare these results, right. So, we have overall E is root node A equals to 0, overall E root node B is equal to some positive number. So, which means again we will be choosing that feature as root node where our overall E is the lowest after branching, right. So, in this case gene A should form the root node with the criteria being gene A greater than 40. Okay, so, as you see now gene impurity or entropy, they give us the same results in this case, in this example. The third criterion, the third measure that we can use for this classification or for this decision is called something called information gain, and this is defined slightly differently and it is based on entropy calculation. So, the first thing we have to calculate is entropy of the parent. Okay. So, entropy of the parent means the parent data set, right. So, in our example this will be the whole data set, right. Now, if you are going into branching, right, here we have just one, we are discussing one branch. As you go down the tree, your at each node the parent data set will change. So, you have to calculate the entropy of that parent and the branches, right, after branching the node, the entropy of the nodes. Okay. So, here information gain is simply entropy of the parent minus entropy of the node 1 plus entropy of the node 2. These node 1, node 2, they are generated after branching. Okay. Here the criteria is the feature that leads to the highest information gain forms the root node, right. So, this is a slightly different criteria, but we will see whether this gives us the same results in the same data set. Okay. So, here is the data set again. Here we again have 5 data sets. We have the cancer types, we have gene A, gene B expression, and first we have to calculate entropy of the parent node, right. So, since we are deciding the root node first, so the parent node means we have all data, right. So, all data we have two classes. So, we are simply calculating entropy of the parent node, which will be simply given by minus summation pi log pi, right. So, we have 2 data points that belong to one class, we have 3 data points that belong to the other class, and that is why we have just 2 terms here, right. So, minus 2 by 5 log 2 by 5 minus 3 by 5 log times log 3 by 5, and we calculate this and we have some positive number again, right. So, here it is 0.29. Okay. And again we try out the same criteria, right? First we consider gene A as the root node and the criteria B gene A greater than 40. Okay. So, what happens is, again the branching we have seen, right? Again we have no branch and yes branch. In no branch we have patients 2, 3. We have then in node 1 we have only one class BRCA, and in node 2 we again have one class LAML, right? This is something we have seen because we are using the same criteria for branching. So, for node 1, now the E1 entropy 1 is 0, as we have seen. For node 2 entropy is 0, right? We have seen this before. What you have to calculate is the information gain, right? Not the overall entropy, but the information gain. So, information gain, if we choose root node A, is the entropy of the parent, which was 0.29 minus 0 here is 0.29, right? That is the information gain if we choose gene A as the root node with the criteria being gene A expression greater than 40. Let us now choose gene B as the root node, right, and the criteria will remain the same, right, where gene B is greater than 30. On this data set we have seen this branching already. So, in node 1 we have patients 1 and 5, only one class LAML, but in node 2 we have two different classes BRCA and LAML. Okay. So, what we have to calculate, keeping this tree in mind, is again node 1 entropy and node 2 entropy, which we did before, right. The values are again E1 equals to 0, E2 equals to 0, E2 equals to some positive number non-zero, which is 0.28. So, we have to calculate information gain now. For if we choose B as the root node, and the information gain is for the parent node is 0.29, here is 0.28, right, 0. So, 0 plus 0.28, so it is 0.28, and the information gain is 0.01. So, if we compare these two situations, is information gain, if we choose A as the root node and the specific criteria, our information gain is 0.29, and if we choose B as the root node with that B greater than 30 as the criteria, we get information gain is equal to 0.01. So, what we have told about is the feature that gives us the most information gain should be the root node. So, in this case gene A should form the root node with gene A greater than 40 as the decision criteria. So, as you have seen, right, all three measures actually gave the same results, which is actually not surprising because they are supposed to give the same results. Now, this is for classification tree, right. So, we are actually dealing with these cancer types, and this is what we are interested in. How do you decide that what should be the root node for a regression tree? Okay. The idea is actually very simple, is we use something called sum of square residuals. We have seen this before, right, the residual information in linear regression. The residual is defined by epsilon I equals to y n minus y a hat. So, y a is the actual value, y hat is the predicted value, but this time from the decision tree, okay, not from the linear regression, but from the decision tree. So, this is the residual. So, sum of squared residuals, and when you can minimize, right, the feature that leads to the lowest sum of squared residuals should form the root node. Okay. So, now apply this to a slightly different data set. So, what we have here is, instead of the cancer type, we have just replaced that with a drug dose. Let us say, imagine these patients, their drug doses will be different, actual drug dose that will work for certain disease, etc. And we will keep the decision criteria as the same, right. So, we use, so this is drug dose is our response variable or the dependent variable that we want to predict using a tree, decision tree. So, this is called a regression tree, and then we have gene A and gene B as features. So, first let us use the gene A as the root node and the criteria B gene A greater than 40, okay. And then again we have very similar structure, right, yes and no. This is something we have seen. Again we have patients 2 and 3. Now, instead of the cancer type, we have the dose information here, and for node 2 also we have the patients 1, 4, 5. Instead of the cancer type, we have the dose information. Now, what will be the predicted dose for node 1 is simply the average value at that node. Okay. So, here for node 1 the average value is 25, for node 2 is average value is 25.67, and that will be the predicted value for node 2. Okay. Now, what would be the sum of squared residuals? Now, if you consider, let us say if we take the patient 3 data and we say, okay, we will predict patient 3 will form in this node, and the dose value is 25, because average value will give us the predicted dose. How much error are we making, right? This is where the sum of squared residuals come into play, right? By these predictions, how much is the error in this data. So, this is how we will calculate sum of square residuals, right. So, residuals we know the predicted dose is 25 for node 1 and for node 2 is 25.67. We are taking this square and just summing them up, so, right. So, we can get a number here. Okay. So, this is if we choose gene as our root node and expression value greater than 40 as our criteria. Now, let us use gene B as the root node, right, as before, and the criteria be gene B greater than 30. We keep the criteria same as before, and we have similar tree structure as before. Again, we have now replaced these values, replace this cancer type information with the drug dose values for these patients. Okay. And we can again calculate this predicted dose for node 1 is the average value for 27.5 and 24. And from what we now want to do is going to predict this or calculate this sum of square residuals, which is simply given by this. So, for each node we will calculate the sum of square residuals, right, taking the average value as the predicted value, right, and the actual values are there. So, we get again sum of square residuals as 468.5, right. So, if we just take this together, right, if we what would be the SSR, right, if we root node is A is about 482 here, and SSR root node B is 468.5, and because we have lower SSR, if we choose root node B and B greater than 30 as our decision criteria, gene B should be the root node. Okay. So, we now understand how we can pick the root node, whether it is in classification tree or in regression tree. The next question that is in your mind probably is how do you choose those values, right? How do you say A greater than 40 or B greater than 30? That should be our decision criteria. We can actually apply very similar principles, right? So, we can vary these thresholds and see where we gain the highest purity, okay? And that might be the threshold for our decision tree, right? So, let us say if you say gene A greater than 20 first, we try that and see calculate the gene impurity or the entropy information for classification tree and see what would be the gene impurity. Then we change that threshold to 30, change to 40 and so on. We evaluate gene impurity at all those threshold values and see where the gene impurity is the lowest and choose that as our threshold value, right. So, very similar idea to root nodes, right. How do we choose root nodes? So, this is how we can go about this, right. So, for classification tree we can simply say highest purity, for example, gene impurity or entropy as our measures for choosing these thresholds or maximum information gain. For regression trees again we can vary these thresholds and see where we minimize the sum of squared residuals, right. So, these two parameters as we have discussed are very important in decision trees, right. We have the root node and the threshold, right, where we actually make decisions yes and no, right, and this can be done by these different measures that we have talked about, like gene impurity, entropy or information gain for the classification trees. For regression trees where we are predicting values, we will try to minimize the sum of square residuals, right. This is what we are after, and based on this we can build the tree, right. So, all the packages, all the algorithms that we are going to use in our hands on, they will be using these methods, some of these methods, right. And now we at least understand how these trees are made, and that is something that will be helpful when you go and try to interpret the results. So, just to summarize, what we have discussed is we can make classification and regression models based on decision trees, and we have talked very briefly about steps of construction of decision trees, right, how we build decision trees. We have talked about the measures of gene impurity, entropy and information gain, and what we will do is we will talk about these advantages and drawbacks of decision trees in the next class, along with some hands-on application of decision trees on some of the real data sets. Thank you.